Okay, so this is the very crucial information. Exam 3 is a week from today.
Right after break will be internal loads?
No internal loads. Right after break. And the topics are everything up through structures. So no internal loads. Okay, anybody have any questions about the test? Yes. Yeah, right. No class on Wednesday and Friday, obviously, too. Yes.
Is it going to be like the same format of like just 2 questions?
It depends what kind of questions, but yeah, most likely because these structures problems are long, you know. Like I would say there are kind of 2 ways I can ask questions on structures. I can do complicated problems and ask you just to give me free body diagrams, or I can do simple problems and ask you to give me, answers. Very often I don't ask you to solve for things. I'll just ask you to derive the equations. But yeah, so be ready for both of those. Like I could give you a question with 6 different bodies in it and ask you for the free body diagrams. And you have to, so to answer those questions, you have to be able to make sense out of what bodies are touching what bodies using, the idea of the joint is part of the lowest numbered member thing. Okay. Or I can do simpler problems and just have you go all the way through it. And likely there'd be one of each, But also be ready for old stuff too. Any other questions? Okay. So what we're doing today is internal loads. We've done some example problems with uniform distributed loads. So now I'm going to do one with a distributed load that isn't uniform. So.
Will we be covering trusses in the exam?
Oh, good question. No, I'm not going to do any trusses on the exam. Okay, so let's say we have a beam with a roller at the right end and a pin joint at the left end. And there's a distributed load acting on it like this. And let's say that the beam has a length of 3 meters. And the maximum value of the distributed load is 1,000 newtons per meter. And we're going to neglect the weight. And calculate the internal loads.
And that's saying like at the max down, there's 10,000 newtons per meter.
1,000, yeah. Right.
Just on the far right.
Right. So the first thing we have to do is calculate the external loads. So I'll take the whole beam. And since I know I'm isolating the whole beam, I can go right into calculating, to representing that distributed load as a point force. We have this right triangle with a length of 3 and a height of 1,000. So the centroid is 2/3 of the way from this side. So, this is 2/3 of 3. So 2. And the area of this right triangle is the base times the height divided by 2. So 1,500 newtons. So for the free body diagram of the whole thing, we have a force vector from the pin joint, an upward force I'll call RB from the roller, and then a downward force of 1,500 from the distributed load. And I'll put my about point here. And of course, you could write out the table, use that to calculate the force, to get the forces and the moments, and use Newton's laws. But I'm going to use, since this is horizontal, I'm just going to go think through it one by one. So Newton's second law, we have RAX, RAY plus 0, negative 1,500 plus 0 RB is equal to zeros. And then for the moment equation, there's no moment about the red dot by RA. For the 1,500, there is a moment arm of 2, a force magnitude of 1,500. Bless you. And would that make this rotate clockwise or counterclockwise around the about point? Clockwise, so this is negative. And then RB, we have a moment arm of 3, a force of RB. Would that make it rotate clockwise or counterclockwise? Counter, so this is positive. And so from these, we get that RB is equal to 1,000 and RA is equal to 0 for X and 500 for RAY. Okay, and one thing I'm going to do here that I think sometimes helps you keep your thoughts organized and stuff, I'm going to just put back in a free body diagram of the whole thing. You can think of this as like the starting point of the internal loads. So we have an upward force of 500, an upward force of 1,000, and we don't have a point force. That's like a fictitious mathematical thing that we use just to do these calculations, but this is what we really have. Okay. So now we have to think about how many cuts we're going to need.
Isn't it just one?
Yep. So we know we always have there's always going to be one cut. You can't have 0 cuts. And then, so now in between the two endpoints, you're looking for places where there are point forces or point couples or changes in the distributed load function. None of those things happen between the endpoints. So this is just going to stay with the one single cut. Okay. So,
So we don't turn it into a point. We don't turn into a point force.
Only once you choose your cut. So we will eventually, but you don't do that while you're trying to figure out how many cuts you need. Okay. So between the endpoints, there are no point forces, point couples, or distributed loads. So we only have one cut. And for that cut now, let's figure out what the function is. So let's find what our function Q is that represents the height of that distributed load at any given X. Okay. You can see that it's a line. So our Q is going to be equal to mx plus b. What's the y-intercept of that line? 0, because when x is equal to 0 on the left end, the height is 0. So this goes away. And so this is equal to the rise over run. So 1,000 divided by 3 times x. So 333.3 repeating x. So for any x value between 0 and 3, if you plug in the x, it'll tell you how high this distributed load is at that point. Okay. If you plug in 1.5, it'll give you 750. That's not right. It'll give you 500. That was bad dividing. Any questions about that function Q? So what we should see at the end, if it works out, is that our derivative of v with respect to x equals that Q. That's one of our checks that we have at the end. Okay, so now we're going to do our cut. And this is valid for any x's between 0 and 3, not including the endpoints of that interval. And so I'm going to do this thing where I draw what we're including and what we're not including. So we have some amount of this distributed load, but we're skipping a lot of it too. We have the 500 here. We're skipping the 1,000. And then we have the internal loads, T, V, and M. Okay. So now notice here's a pain that we have. So in order to represent that distributed load as a point force, we need to know the height of that triangle. When we isolated the whole thing, we knew that the height was 1,000. But it's not 1,000 anymore. You know, this is some arbitrary distance x. And the height of that distributed load at the right end is going to depend on what that x value is. So how can we represent the height of that distributed load? This is the first time that we have to use that Q function. Yep, it's equal to Q of x. So the height here is 333.3 repeating times x. Are you with me on the reasoning for that? Okay, so now, in order to do the calculations, we have to represent that as a point force. So let's draw the triangle and start calculating the centroids and all that stuff. Okay, so first of all,
2/3 x.
yep, perfect. So from the point of that triangle, it's 2/3 of the base of the triangle. The triangle's base is x. This is x. So this distance is 2/3 x. And now what about the area of that triangle? The base is x. The height is 333.3 repeating times x. And so the area is x, the base, times the height, divided by 2, or 166.6 repeating x squared. And so now I'm going to draw this free body diagram again with that distributed load represented by its equipolant point force. And so that is a downward force of 166.6 repeating x squared. We still have the 500 Newton force and the internal loads. And our distances, so this distance is 2x over 3. This distance is x. And now we can go to Newton's laws. So Newton's second law says 0, 500 plus, this is a downward force of 166x squared. So you can think of that as 166x squared times the unit vector 0, negative 1. It's facing downward. So this is 0. What?
Just scroll back up to the triangle.
Can you explain that one again, why you multiply by the unit vector?
By what?
By the unit.
Yeah, okay, so you can always think of, so anytime in a free body diagram that you have an arrow with a value associated with it, you can represent that vector as the unit vector in the direction of the arrow times the value. Okay, you've done that a million times with cosine and sine, So you can multiply cosine of 30, sine of 30 times 750, and that gives you, a vector in the direction 30 degrees with a magnitude of 750. This is a vector in the direction downwards with a magnitude of this. Okay, so we're going to take this and multiply it by the unit vector in the direction downward. Well, what's a unit vector in the direction straight down?
0, negative 1.
0, negative 1. And what you get there is,
And you do that just to make all the calculations easier, or that?
yeah, just in case, it's easy to get yourself turned around backwards on some of this stuff. So it's nice to have some things that are true in the back of your mind, Yes?
For V, is V the magnitude of that vector put through times the,
Right.
so if V is, if it was negative, would be pointing up,
Right.
and if positive is pointing down.
Correct.
Okay.
So the second vector is 0, negative 166.6 repeating x squared. That negative is because it's down. And then you have plus, I'll lump these two together, t in the positive x direction, v in the negative y direction. is equal to zeros. And so t is equal to 0, and v is equal to negative 166.6 repeating x squared plus 500. And now the moment equation. So my about point is at the left for all of these cuts. The 500 doesn't produce a moment. The downward 166x squared has a moment arm of 2x over 3, a force magnitude of 166.6 repeating x squared. And would that make it rotate clockwise or counterclockwise around the about point? Yep, clockwise, so it's negative. And then we have the couple. And a clockwise moment from v times its moment arm of x. Those always appear as minus vx equal to 0. And so this gives us that m is equal to vx plus, so 333 divided by 3, so this is 111.1 repeating x cubed. And now we're going to substitute in what we know v is. It's this function, and we have to multiply it by x. So m is equal to 166.6 repeating x cubed plus 500x plus 111.1 repeating x cubed. That comes from this first term right under Rn2L. So 2 times 166 is 333, divided by 3 is 111. And now you get some cancellations here. And we come up with a function m that's equal to negative 55.5 repeating x cubed plus 500x. And these functions are valid on the interval x between 0 and 3. And the last thing that you should get in the habit of doing after every cut is do those derivative checks. So the first one is dm dx should be equal to v. So dm dx is negative 166 x squared plus 500. So this one works. And then the second one is negative dv dx, bless you, is equal to q. Negative dv dx is positive 333.3x plus 0. And that was our q function. So this one works too. And that gives you some, a bit more confidence in your answer. Like I said before, it doesn't guarantee that you didn't make a mistake. It just guarantees you didn't make a mistake from when you got your v function to calculating that moment. Yes?
Why wouldn't you just then take repetitive of things to find your handle.
Yes, right. Well, what you would have to do, so
Would have, if you were to integrate, you'd still not know the options.
so you could do, yeah, so you could get your Q function and then integrate once would be the idea to get your V function, and then integrate again to get your M function. And it's true, you can do that. But yeah, just like you said, there are constants of integration at the endpoints of all of your regions, at the ends of all of your subfunctions. And you would have to get those to match up with boundary conditions. So yes, you can do it. It's not terrible, but it tends to be no faster than this. And then you wouldn't have any way to check your answer at the end anyways. So I think it's a better way to go to just use Newton's laws, and then you have the two derivative checks. Yes?
What happens to that 1,000-Newton force on the end?
Yeah, so yeah, in a way, so that kind of thing can be kind of confusing because it's like once you go to the cuts, you're never mentioning that. Like that has to affect the problem somehow. But remember that when we calculated those internal loads, that endpoint force was like baked into the problem from that point on. We already calculated it, and it affected our 500 over there, you know? And so it's like influencing the problem behind the scenes at that point, you know?
Okay.
And so I recommend just always doing it working from the left to the right, because then you get used to doing it and you're less likely to make mistakes. But you could work this problem from the right to the left. And if you did, you would get all the same answers.
So our goal is essentially to isolate like single point forces into like regions. So like we have that 500 in a region, and we do that region. If there was like some other end past the 1,000 and then something.
Yeah, then we'd have to include it. But remember that the things we're isolating always go from the far left end of our chosen body to some X value. So don't think of it as like we do this cut and then we do this cut. It's like we do this cut and then we do this cut. Yes?
So you said it was non-uniform.
Yeah.
Like distributed.
Right.
But, so it is non-uniform through the whole, beam?
In this case, yeah.
Okay.
Okay, let's do a harder one. And before I do the harder one, well, maybe let's, okay. Question. What makes this a harder problem? So let's say that instead we had a pin joint here and a roller here, and this is 3 meters. And we had a distributed load like this. I mean, that's the exact same problem as this, just flipped around backwards. Right? But if we're going to actually work this problem as it's drawn here, think of what a cut would look like. You would have this, And you'd be leaving off this amount of stuff.
A slightly more difficult function to use.
Right.
Intercept is a 0.
Could we do it from the other direction, right to left, so remain a triangle versus a trapezoid?
Well, let's see, this is 1,000. So, okay, so yeah, the issue here is now instead of being a triangle, this is a trapezoid. You know the height of it. It's not impossible. I mean, I used to make people learn how to do this, but it takes a while and it's tedious, you know. You can think through the geometry of it. Basically, the way you have to do it is think of it as two different distributed loads happening simultaneously, you know, do them independently. You have a right triangle here and a rectangle, and you can just treat each one of those, come up with the equipolant point force for each one of those, and then just do both of them. It's just a little bit of a pain. So like a better way to do a problem like this, if you ever see a triangle where the edge is on your left side and the point is on your right side, the better way to do it is just imagine walking to the other side of the beam and do it backwards. You know, like that's easier than all this trapezoid stuff.
And the problem with just doing it from the left hand is then you mess with all of your, the steps you normally take, and so you're more likely, if you have a.
That's right, exactly. Like I would always work from the left side of problems just because you'll most likely make dumb mistakes since going the other way because you're not very used to doing it, you know. So I would always work from the left side, but if you see a triangle with the edge on your left and the point on your right, then I would just flip the problem. Just imagine looking at it from the other side and then work from the left. So instead, just imagine looking at the beam from the other side. It's good exercise to walk to the other side of the beam. That's how I got this body that you see before you right now. Okay. Yes.
You come up with the same answers either way.
Okay, so yes, you come up with answers that represent. So what? That's a really good question. So how would your answers compare to some? So somebody does this, just the straight ahead brute force approach. They do the trapezoids and they come up with their answers. You imagine walking to the other side and you end up doing the problem the way we just did it. How will those two answers compare? Well, the functions will not look the same. The reason is your x equals 3 is their x equals 0, and your x equals 0 is their x equals 3. But if you choose any physical point and use your functions to calculate the internal loads at that point, the answers will match.
Won't the functions be the same except for a vertical shift?
Well, no, I mean a horizontal shift.
Yes, horizontal.
They will be, I guess they'll be horizontally shifted and then flipped also.
Oh.
Yeah.
But you could.
You could do the, yeah, I guess, the math curriculum now I think does a little more of that like flipping and shifting type stuff than than when I took those classes, but yeah, you could apply that stuff. But the key idea is, if you want to use that function to calculate the internal loads at a point, you do that, they do that, those answers will match. Any other questions about that? So no trapezoids. I even used to have a problem where there was a triangle going one way and a triangle going the other way. So it was like you were trapped. You had to, but then it's like, well, just you could do one half one way, or what's the odds of that happening anyways? If that comes up, then okay, take the time and figure out how to do the trapezoids. But that's a pretty unlikely thing to come up, I would say.
Like a suspension bridge or something? Like,
Yeah.
you have like the cables going in opposite directions.
Right. But those aren't distributed loads. Those are just a lot of point forces.
Question.
Yeah.
Could you just figure out the Q of X of the tracker? The graph of Q.
It's a little more complicated than that, but I mean, that's part of what you have to do. But then,
Okay.
so yeah, I mean, if anyone's interested, I mean, and you have time, whatever, like try it. You probably can work your way through it, but it's just tedious, Like, I don't like doing it either, Okay.
If I ever come across a problem with the two triangles, I will write a computer program.
Yeah, I think that's the attitude to take, to be honest. Like, all this stuff I'm teaching you is stuff getting you ready to write computer programs to solve problems. Like, I really doubt there are any companies where people sit at desks and do hand calculations of this stuff. And if they do, I don't know what they make, like iron boilers for steam engines or something,
Well, and I mean, at least personally, I wouldn't trust the number from a person. As
Yeah,
much as I would trust the number
exactly.
from a computer.
Exactly.
Sort of thing. There's enough little places to make mistakes.
For sure. Okay, well, am I going to start? No, let's just stop there. So Thanksgiving starts now.
Thanksgiving starts next.
Yeah.